Thank you, Anne, for that very kind introduction, and thank you to all of you for being here today. So my hope today is to educate you all in the matter of synthetic fuels, and we'll define what synthetic fuels means, at least for the context of today, in just a moment. But I want to at least mention up front that I'd be very encouraging and very happy for anyone to fire away questions at any point during this talk and during this presentation. In fact, this isn't really a talk. I view this as really as if I were teaching any class here at Stanford campus, where the more involvement from the students, you in this case, the better, as far as I'm concerned. Okay, so feel free anytime, raise your hand and ask any questions. So let's start with the goal for today. The goal for today is to discuss, and this is how I'm pretty much defining synthetic fuels for this context, is to discuss unconventional emerging technologies that could produce fuels in a renewable, sustainable manner. Okay, that's what I mean by synthetic fuels for the context of today, and I'm going to explain why in a moment, why I'm defining it this way, because really synthetic fuels is a very broad term. I mean, it means synthesizing a fuel, and you could argue that hydrocarbons that we're getting from the ground, petroleum that we get from the ground, I mean, if we put that petroleum, that crude oil straight into our cars or trucks, those vehicles are going to die in a heartbeat, right? So you could argue that you actually synthesize fuels from those feedstocks. And so there's a lot of shades of gray here in terms of defining synthetic fuels. So this is how I want to define it today. And some of the key terms here are really renewable and sustainable. I also want to point out, so some of you in the audience might have already taken a look at some of these previous GCEP Energy 101 tutorials, but these videos are all posted online, the slides are posted online, and these are three that I think are particularly relevant to the themes I'm talking about today. So those of you here in the live audience, if later on you want to kind of reference back to some of this material, I would recommend going to Solar Energy 101, which was talked by Nathan Lewis a few years back, Solar Cells 101 from Mike McGee, and I gave a tutorial on Electrocatalysis 101 about 2 years ago. Okay, so and for those of you who are watching this video, you might want to pause it and go to those particular tutorials right now and check those out first. Okay, this is the outline for today. So first and foremost, I wanted to talk about fossil fuels. I just want to make sure that we're all on the same page as to what fuels are and where they come from conventionally, and then we can start talking about these more unconventional and emerging and exciting directions. So we'll talk about fossil fuels first, then talk about pathways to renewable synthetic fuels. We'll talk about thermodynamics and efficiency. Of course, when you're talking about energy, it's pretty important to have a bearing on both of those topics. And then we'll kind of get into more of the technology, and we're going to focus in on these electrochemical and photoelectrochemical pathways. And I'm going to talk about why I think those are particularly interesting for this case. We're going to do a lot of our discussion on hydrogen fuels, and a big reason why is because a lot of the physics and the chemistry and the materials and the technology have been developed in that domain much faster than for synthesizing carbon-based fuels. And so this really serves as a really excellent launching point. Everything that we've learned here can be then extended to carbon-based fuels. And so that's kind of how we're going to wrap things up at the end. And then we'll summarize. So let's get into some facts of the matter. This slide is coming from the International Energy Agency. This is from 2013 report, just looking at the key energy world statistics. This is a wonderful document for any of you who are not aware of that. I would highly recommend going to the IEA's website and downloading this. It's about 100 pages long. It just gives you wonderful technical detail as to how energy is produced and consumed across the globe. So this is just one example of the type of information that you would find there, just a tip of the iceberg, but a pretty important part of that iceberg, where I think the main points I want to get across are that, first of all, we're consuming about 17 terawatts of power. Okay, that's the global consumption. And very importantly, 80% of that is coming from fossil fuels. Okay, so it's one way you could define a fuel, right? Fossil fuels, you've got coal, you've got natural gas, you have oil, solid, liquid, and gas. The nice thing, or I should say the convenient thing about looking at this analysis is that if you just look globally speaking, oil, coal, and natural gas all provide about 1-to-1-to-1 energy across the globe. It's not quite exactly that, but if you can just remember that, you've got a good first order approximation. And of course, we know that the amount of energy consumption is continuing to grow. So I think one of the main points I want to make from this slide is that fuels, okay, if you want to define them as the fossil fuels, this is the dominant form of energy across the globe. And therefore, if we could produce these types of fuels through a more renewable and sustainable manner, that's one way that it's kind of already plug and play with our entire infrastructure and avoids all the issues that we know that fossils bring with them. Okay, so that's why synthetic fuels are interesting, generally speaking. Let's talk about fossil fuels in just a little bit more detail here. And I want to go through a few thoughts of mine on why I think fossil fuels are so wonderful, actually. So let's consider petroleum and gasoline. So first of all, we know it's a massive worldwide resource, right? We know that if it's 17 terawatts is coming from fossil fuels, and it's about 1 to 1 to 1 of oil, coal, natural gas, and that's 80% total, then about 5 terawatts is coming from petroleum. Okay, that's a massive amount of energy. There's always concerns globally about, are we going to run out, et cetera. But my goodness, we use it quite extensively. It also has a massive energy density. Okay, I mean, if you really think about this, you can drive a car about 500 miles on just one tank of gas. And I'm not talking about some super massive gasoline tank car. This is like a Toyota Camry, right? Honda Accord can drive about 500 miles. They have like 18-gallon tanks these days. And of course, you can fly a commercial jet halfway around the Earth. Right? If we needed to get to Frankfurt, if I needed to get to Frankfurt in 15 hours, I could just race to SO4 right now and probably catch a Lufthansa or United flight and there without refueling, stopping, or anything. It's amazing how much energy you can put into these vehicles. A full tank of gasoline in a car is approximately equivalent to the potential energy of 1 million gallons of water sitting 200 feet above my head. You can imagine that crashing down on us right now. It's also about the electrical energy stored in 80,000 iPhone 6 batteries. Just one tank of gas, right? Just one car. Again, like a Toyota Camry. It also has a huge power density. It's not just got a lot of energy, it can deliver that extremely quickly. So for instance, right, we know we can power automobiles and trucks and shipping vessels, commercial and military aircraft, right? You can go several times the speed of sound. Here's also something really interesting, the power transfer and filling up your car at the pump, right? You're just sitting there, you're filling up your gas tank, and you're like, kind of like, oh, what a waste of time. You know, I want to get back onto the road, is probably what you're thinking. There's about 5 megawatts, if we were to convert that into electricity units, of what's flowing into your gas tank, like right through your fingertips as you're holding onto that pump. And just to put that into perspective, a typical nuclear power plant in the United States, garden variety size is about 1 gigawatt. So that's like 200 Honda Accords getting filled up at the gas tank is equivalent to the power output of a nuclear power plant. That's how fast that energy transfer is, because you've got this huge energy density that's in these chemical bonds of the fuel, and it's flowing in at about 6 gallons a minute. Yes, sir?
I think a bullet train or a high-speed train runs at about 7 megawatts, which is just about that same number.
Okay. I'm not aware of that number, but that's a good tidbit to bear in mind. Yeah?
500 people on it.
Yeah, that's right. Maglev or standard? Maglev. Cool. And yet, despite this massive energy density and power density that you find in these chemical fuels, they're completely stable, right? We drive around, these are bombs, right? And that much energy density, that much power density, and yet we're not scared to get in our car and drive away because we've engineered it to be safe. So they're very chemically stable, which is something that's really convenient. It's also very easy to store and transport. You guys might not realize it, but there's about 100,000 miles of gasoline pipeline in the United States. 100,000 miles, right? I mean, coast to coast, it's like 2,500 miles, right? So there's 100,000 miles of gasoline pipeline. It's a liquid. It can fit into any size and shape of container with ease. What about cost, right? Obviously, many of us in the room, I would say, now looking around the crowd, I think all of us were around when gasoline was about $1 a gallon, and now it's $3.50 or so a gallon, $3 to $4 a gallon. We might say, oh my gosh, prices are going up, it's getting really expensive. But if you really think about it and you want to reference it to other consumer goods, you know, even bottled water at the store is $1 or $2 a gallon, right? A gallon of milk around here is about $3 a gallon. So a gallon of milk and a gallon of gas are about the same price. Gallon of orange juice is definitely more expensive than gasoline, right? And if I had to choose between a gallon of milk and a gallon of gasoline is way more helpful for my life, for me to do what I need to do, than a gallon of milk. Although I do have 2 small children, so for them maybe it's a different story. But and then there's convenience, right? You have all this, and then the convenience. I just mentioned, you know, nobody's really thrilled to go to a gas station, but has anyone here, just raise your hand, I'm curious, has anyone timed themselves at a gasoline station? No? That's what I do for fun. Yeah, that's what I do for fun, right? I mean, what else are you going to do? I get there, and I try to set a personal best, right? And so I get in there, and I pull out my credit card, and I'm like trying to be fast, and it takes me 3 minutes. 3 minutes from the time I hop out of my car, I've paid for the gas, I punched in my zip code, I stick it in, I fill up my tank, and I pop it back in. Remember, it's 6 gallons a minute. right? So if you have a, say a 15-gallon gas tank and you go in there when it's, maybe at a quarter tank left, I mean, that'll take less than 2 minutes probably to fill. So it's actually really, really fast. So 3 minutes in and out of a gas station, how much time, if you had no life on your cell phone battery and you plugged it in for 3 minutes, what would that give you for talk time? Yeah, you'd be lucky if you could even turn on your phone on 3 minutes of plugging it in. And that's a very low power device. Here, I go from an empty gas tank to be able to drive to Los Angeles for 3 minutes, right? So these are all the wonderful advantages of fossil fuels. And so, it's no wonder why we consume so much petroleum. It's also why these things are so hard to beat. I mean, fuels are absolutely amazing and spectacular. And of course, they just come with a lot of baggage. There's a lot of problems with fossil fuels. And so we have to find other means of using energy, producing energy, converting energy. But this also motivates, hey, if you could produce a fuel that can do all of this for you, but not have a CO2 issue, not have climate change issue, not have geopolitical issues, boy, that would be a nice technology to have. And that's exactly why we're having this session today. That's exactly what we're talking about, is new routes to these types of chemicals without all the baggage from fossils. Okay? All right, so let's talk about what these chemicals look like. So everything that we talked about with coal and oil and natural gas, to to the simplest, I would say the simplest description I would give, if I were talking to, let's say, a 5th grader, is it's just a bunch of carbon and a bunch of hydrogen mixed together and as chemicals. Okay, those are the two main ingredients. And there's a lot of carbon-carbon bonds and carbon-hydrogen bonds. Now we're going to escalate it to high school chemistry, carbon and hydrogen bonds. When you start ripping out these bonds, that's where you get the energy release. When you burn these things, you get the energy release that allows us to drive our cars. The interesting thing about these is, this is class of compounds that are called hydrocarbons for obvious reasons. They have hydrogen, they have carbon. And here we're looking at pretty much the difference between natural gas. These are the more kind of liquid fuels, gasoline, diesel. Here's motor oil, plastics, like your milk jugs are made out of this type of material. And coal is kind of similar to what you see here, although it's more two-dimensional in nature, but it's basically a bunch of carbon-hydrogen bonds. So it's really the same type of bonds that you're burning for all these types of fuels. These are really small: methane, ethane, propane, butane. Again, this is what you get out of natural gas reservoirs. They're so small that gives them the physical property that they're gases at standard temperature and pressure. If you start building them up and start linking them, then you get more liquids, and then ultimately you get to solids. But really, at the end of the day, it's the same type of molecule. So these are the type of molecules that provide all those services that we were just describing. How do we get them? We, of course, get them from the ground. We grab oil that comes from underneath, and it's not like there's this big swimming pool of oil down there. Okay, these are basically rocks. These rocks are very porous, and infused inside the pores you have these types of molecules, and we just find clever ways to basically flush them out from inside these pores of the rocks. We pull them out, pump them out, and then we put them into an oil refinery, which is absolutely one of the most spectacular examples of modern technology. When I was growing up, I used to see things like this, and I thought they were just the ugliest thing. It's just a bunch of concrete and metal. But now I realize what they do and how well engineered they are. I mean, one single facility can take in 150,000 barrels a day of crude and do all the chemical processing needed to make them usable in all these different technologies, whether it's a diesel truck or an aviation, a jet, or a car, or for asphalt, or what have you, or to grab sulfur, for instance. It's amazing. And so these chemical plants are extremely important. There are about 700 refineries worldwide. 700, each one takes in on average about 100,000 barrels of oil, just to give you a sense of scale, right? So we do this every day without even thinking, because they're optimized and engineered so well. It's really a marvelous technology. In fact, so here's some recommended viewing for you. I can promise you this is worth your time. To go check out on the History Channel, they have this Modern Marvels series, and they have done at least a couple on oil, one called Gasoline, which came out in 2002, another one, The Secrets of Oil, 2008. And it's just a wonderful way to catch up to speed as to what these molecules are and how these conventional processes work, what we can do with it. It really is spectacular. What if you wanted to synthesize, let's say, diesel or gasoline, but you couldn't use petroleum? Okay, again, this is another definition of synthetic fuels, you could say. And I would call it a more conventional approach to synthetic fuels. Basically, if you can make carbon monoxide, CO, and hydrogen, H2, we have large, well-working industrial modern processes that can convert that carbon monoxide and hydrogen to make just about any liquid fuel that you'd want. And so, if you really wanted to, you could certainly grab something like coal. You could even get biomass, right? You could basically grow plants and things and feed them into a process where you effectively make your carbon monoxide and hydrogen. Then you use another reactor for water gas shift. And then you can do what's called Fischer-Tropsch and some product upgrading, and out the door come out things like naphtha, diesel-type molecules, all the things that we would conventionally get from petroleum. What I'm showing you here already exists at the large scale. There are plenty of plants around the world, chemical plants that are $10 billion, $20 billion investments that can do exactly that. You can feed them in, feed them biomass, you can feed them waste, you can feed them natural gas, you can feed them coal, and they can basically make these liquid fuels. Yes, sir?
Could you briefly explain what water gas shift is?
Sure. Water gas shift is if you feed CO and H2, CO2 and H2, you can shift the stoichiometry from CO to CO2, balancing out hydrogen and water. So the reaction is, I should have written it out. The four ingredients here are carbon monoxide, carbon dioxide, H2, and H2O. And so this is a way that, for instance, you can, if you feed in CO2 and H2, you can basically grab one of the oxygens from CO2, make water, and then you get CO coming out. Or you can feed in CO and H2O, and you can grab that oxygen and stick it onto the CO to make CO2 and get hydrogen out. So it's a way of shifting the equilibrium and shifting the balance between carbon monoxide and carbon dioxide, and the other side of the equation is going to be H2 and water. Okay? And so that's just, and so this is kind of for this particular case, it's just kind of a technical detail, because when you do this, it's a massive reactor. I don't mean to trivialize it, but when you gasify different sources like coal and biomass, you're going to get a natural stoichiometry coming out of carbon monoxide, carbon dioxide, hydrogen, and water that might not be the appropriate stoichiometry that you need to ultimately make the products that you want. So you use water gas shift to kind of tilt the balance in your favor and then send that along the chain. So this unit here is really designed. That's where the flexibility comes in, where it almost doesn't matter what your source is coming in, because the sources coming in are going to identify what's coming out of this unit, and then this kind of gets things set up so that everything can go downfield okay. Yes?
How is that different from steam reforming? Or is it?
Steam reforming is a process that's typically talking about, so it's hydrocarbons coming in. So steam reforming would actually fit into this box of, this is gasification and reforming, where you're taking, that's what's going to produce your CO coming out here. So when you reform methane, for instance, you're producing the CO and the H2 that then goes into the water gas shift, and then the water gas shift will tilt the balance how you want it, such that it can do the rest of the chemistry to make the product you desire. Excellent. Great. Okay, so those are conventional processes. Let's just kind of take a look at the map of these different fuels that one might want to make. So this is volumetric energy density, megajoules per liter, plotted against gravimetric energy density of megajoules per kilo. And so here's diesel and gasoline, and as you can see, they're phenomenal on both metrics. Right? They're very, very great fuels from an energy content. I already described how wonderful they are in terms of energy density. Batteries are down here, just so you know. And by the way, I'm not trying to say that fuels are always better than batteries. I think in this game of energy, you can't just put all your chips into one bucket of possibilities. And I think if we're ever going to compete with fossil fuels globally, this is now where I'm going to go into like more of a personal opinion on the matter. I don't think we can look for that one silver bullet that's going to take care of everything. I think we need a combination of technologies. And batteries have a tremendous role to be played in all of this. But if you want to look strictly in terms of energy density, clearly these chemical bonds in hydrocarbons are much more rich, and the chemical bonds in hydrogen as well. So HH bonds are fantastic sources of energy. You can see on a gravimetric density basis, they're huge. But on a volumetric energy density, they don't compare nearly as well, because hydrogen obviously doesn't want to be in the condensed phase. It much prefers to be in a gas. Okay, whereas these are very natural liquids. So everything you see here, diesel, gasoline, coal, methanol, and hydrogen, that we produce, everything except for ethanol, all these other chemicals, these are all coming from fossil fuels today. All right, that's the modern, so any hydrogen that comes around, we'll talk more about hydrogen in a bit, but that hydrogen is really coming from the ground ultimately. It's coming from natural gas usually. Ethanol is the one exception. Ethanol, there really is no good industrial process to make ethanol from syngas. So I talked about that on the previous slide. If you can make carbon monoxide, you can make hydrogen. No problem making things like methane. You could even make methanol. You can make diesel and gasoline, but it's really hard to make higher alcohols, ethanol, propanol, butanol, and things like that. So ethanol is actually made through the process that we all know of fermenting feedstocks, food feedstocks like sugarcane or corn. That's how we get our ethanol. If you're in the US, your ethanol comes from corn. If you're in Brazil, it comes from sugarcane. And those are by far and away the two leading nations in terms of ethanol production. Okay, so these are the types of fuels that we would love to be able to make through more renewable, sustainable processes. I should also point out with ethanol, by the way, while today we are making it through something that is in principle a sustainable process. We're growing plants that take in carbon dioxide and sunlight and water, and we do get energy out of it, and the net return on energy is positive, right? So you actually get more energy out than you put in. That is running into a lot of problems that this process works best with these food-based feedstocks and agriculture that ultimately is going to impact food somehow or another. And while it's no biggie based on our current consumption of ethanol today, if we were to say, let's replace all the fuels in the world with ethanol through that process, you're just going to run into a huge land problem and a food problem. It's going to be a feeding the world problem. And that's, so making this type of molecule would be fantastic if you could find another path that avoids agriculture. Okay, so this is the broad vision. So those of you who were at the technical talks yesterday saw this slide where we want to make these types of fuels. They're wonderful in terms of energy density. Let's just think of a black box as your typical engineering analysis. You have a black box, you feed it into three things: sunlight, water, and CO2. We know we've got lots of sunshine coming down on the Earth, right? So there's orders of magnitude more energy striking the surface of the Earth than we actually need. So even if we could just grab 0.1% of that, we'd be in great shape. Water, obviously, extremely abundant. We're all breathing it right now. And of course, we're all breathing CO2 as well at 400 parts per million and climbing. So let's say you take these feedstocks, you feed them into this black box, and you're asking that black box to break apart some of the bonds here and reform the bonds there. Then you can make things like oxygen as one output stream, which is a nice, something that we all need, and it's not a bad product, though it actually has very low value because we do get it for free from the Earth. But then these are the things that we conventionally get, again, from fossil fuels that would be really great if we could instead get from these renewable sources. So things like hydrogen, carbon monoxide. In fact, this is pretty much the water gas shift type of reaction that we're talking about. We can make alcohols, hydrocarbons. Okay, these are all very good fuel molecules. So you could, option one is you can use anything I put on this slide plus a whole lot of other possibilities. Any of these things could be used as fuels. Or you could use them as chemical products. A lot of these are important chemical products for the manufacturing industry. Or if you didn't make the thing that you really want, then you could use these things as chemical precursors. So like hydrogen and carbon monoxide, methanol, ethylene, these are what we call platform chemicals. If you can make these chemicals, you can just plug them into the modern chemical infrastructure and it'll crank out whatever you want, just about. So we have a lot of control there. So that's the broad vision. Then of course the question is, well, what's inside that black box? And that's really this question of synthetic fuels, right? This is where it's up to our own imagination, our own creativity. So many different approaches. And that's probably one of the most important things I could relay to you today is that there's no one way to do synthetic fuels. And there's no one way to do synthetic fuels in a renewable way. There are so many different approaches. It doesn't matter if you're a biologist, a chemist, a physicist, an engineer of any discipline, okay, or even a non-scientist, non-engineer. Anyone can think about ways to creatively pull this off. And the good news is that there's lots of ways that have been demonstrated technologically that can accomplish this. Plenty of different ways to do it that have been shown in the laboratory. The question is, what's going to be cost effective, right? Because if it can't compete against the price of fossil fuels, it's going to be a big uphill battle. So some are going to have kind of inherent advantages along that direction compared to other technologies. Okay, so that's very important to bear in mind. So of these many possible schemes, just to kind of whet your appetite as to what some possibilities are, here's an example that's photobiologic. This is from the National Renewable Energy Laboratory, where you can grow organisms, okay, and you engineer their metabolisms so they can produce whatever product that you want whenever, these microorganisms, right? They, like any plant, right? That's what they do. They take in water, they take in carbon dioxide, they take in sunlight, and they grow. But they didn't grow to suit our needs of society's energy, right? They're growing for their own processes, for them to live. And so effectively speaking, they're not very efficient by our definition if we want them to like crank out a given product. And so this is what, this is one approach. You can just make these microbes that they can do that type of chemistry. You can think of photochemical routes where you can engineer molecules so that you shine light in, and here's an example of this ruthenium complex. This ruthenium, you basically excite an electron in ruthenium. And when you excite that electron, it'll transfer itself. It'll transfer itself this way. So you excite that ruthenium, it'll send that electron into methylviologen. The methylviologen gets reduced, and then the methylviologen sticks the electron into platinum, and the platinum goes about and makes hydrogen. Okay, so there's all kind of chemical schemes that you could dream up. You could go with solar thermal. You could take an array of mirrors and focus them on one spot. And typically these types of this is a solar thermal plant. It's not a catalysis plant. It's a solar thermal plant where you're really heating up something like a molten salt. You keep that molten salt stays nice and hot, and then you can run a heat engine off it even when the sun is down because it's such a high temperature and it maintains that heat capacity so well. But you could do conventional thermochemical heterogeneous catalysis. So just like those other processes I was talking about with the syngas to make liquid fuels, you can imagine those all require heat and pressure. This is like another way you can imagine getting heat and pressure with sunlight. You could also imagine just buying a bunch of photovoltaics and buying a water electrolyzer, plugging them together. Okay? If that electrolyzer splits water, you make hydrogen. If it's an electrolyzer that electrolyzes CO2, you can go from CO2 to make all kinds of interesting carbon-based products. Yes, sir?
So for the photobiologic, I was just wondering, do you know what is the cost to make a gallon of gas?
It is very expensive. It is very expensive.
Is that like $7 or?
The numbers I've heard are even more than that. Right. It's kind of more like in the $15 to $20 range. And that's to make, molecules that are certainly fuel molecules. Another thing to consider is that oftentimes what they're making are not necessarily drop-in replacements to what we have today. So that's just another thing to consider. Yeah. But yeah, those are pretty expensive pathways. And so technoeconomics is important for all of these types of schemes. So for instance, you can do that here pretty easily. Like if you're interested in making hydrogen, and again, we'll talk more about it in a moment, but you can pretty easily get the price of solar cells these days. I mean, this is a very well-developed technology that's obviously on lots of your rooftops, I'm sure. And then prices of water electrolyzers. I mean, this is also an old field, a much older field, frankly. Water electrolysis, that was, these things have been sold for about a century, right? Commercializable technology. I can tell you right now that if you make your hydrogen this way, it's going to be more expensive than how we currently get it. So the question is, how can you come up with a better way of lowering that cost? Right? Like I said, it really comes down to cost effectiveness. So, but this is just to whet your appetite. I mean, this is hardly comprehensive, right? There's so many possibilities here, and you can couple these things too. So you can couple thermochemical processes with electrochemical processes with biological processes. There's a lot of ways that you can synergize technologies, and that's just again up to our own imagination and creativity. What I'll be talking about today, because there's a lot to be said about all these technologies, I want to focus on a couple of schemes that I think are particularly promising. And one is very related to what I just showed on the previous slide, which is you take conventional energy technologies like wind and solar, right? These are obviously being deployed massively across the globe already. Can you make a device such that it's cost effective to feed in water or feed in CO2 plus water and then make the fuels and chemicals that we need? And of course, if you can do that, if it came from, let's say, CO2 from the atmosphere, it's perfect, because then you make a fuel from atmospheric CO2, you combust it in the car just like you always would, and then it just goes right back in the atmosphere that you can recapture, and now there's no net emissions of CO2 in that cycle. You're recycling the CO2. That's one way to do it. Another way to do it is to have, instead of two separate devices, you can have one integrated device. This basically looks like a bunch of semiconductors, a bunch of photovoltaics dunked under water with some source of CO2. And then you basically shine light. Your semiconductor does the same thing that this semiconductor does, where you excite electrons. But in a typical photovoltaic, you're running these electrons in the positive holes that are left behind. You're running them around a circuit and getting voltage and current out of it. In this case, you're not running them around a circuit. You're just instantly using that electron and that positive hole to do redox chemistry, to do the chemical transformations needed to go from CO2 to methanol or water to hydrogen. Okay, so these are the two types of technologies I want to focus on. And a major issue with this is making good catalysts for these chemical transformations. Another one is making good semiconductors that can absorb light and do all the processes you need it to do. So let's talk a little bit about that chemistry. And then I want to get into some of the technical aspects for a moment. I will zoom back out and we'll look more into the big picture in a moment. So don't let these slides scare you too much. So what we're looking at is a bunch of reactions that we would like to drive. Okay, and I mentioned the electrocatalysis 101 tutorial that I had given a couple of years ago. So in that tutorial, I kind of went into this in great detail. So that's for those of you who might want to take a look at that if you want to beef up your knowledge in this area. But for now, I'll just kind of go through this so that we can just capture what we need to move forward and understand the big picture better. So if you want to make hydrogen, here's one way to do it. 2 protons, 2 electrons goes to hydrogen. We're going to put this on a voltage scale, which by definition, we're going to define this reaction at 0 volts, meaning that if you had an electrode and stuck it under water at 0 volts potential, then the backwards and the forwards reaction should be going exactly equally fast. And then you can tilt which direction you want it to go, either go protons plus electrons goes to hydrogen, or hydrogen gets oxidized to make protons and electrons. You can tilt it based on where you stick your electrode potential versus that 0. Now here's a bunch of very interesting reactions with CO2. Right? CO2 to carbon monoxide, methanol, some hydrocarbons, some alcohols. Okay, these are all really nice things that we'd love to be able to make from the CO2 and water that we're breathing right now. Okay, so we're going to pay really close attention to these reactions. And then this other reaction here is going from O2 plus protons plus electrons goes to water, or the other way around. You split water and you end up with oxygen and releasing some protons and electrons. You notice that all of these have a characteristic voltage, known as this equilibrium potential. Again, if you hold your electrode at these potentials, then the backwards and forwards is exactly equal to one another. Now, let's plot this up. So here's, on an x-axis, I'm going to plot the voltage scale. And I want to plot these values here. So hydrogen is at 0 on the scale. The oxygen is at plus 1.23 volts. That's 1.23 volts apart here. And then if you look at all these CO2 reactions, they're all very clustered, very close to that hydrogen. Okay, so it's just good to bear in mind. Okay, they're all these values, in other words, are very close to that 0. And so, the deal is that if you want to make these fuels, you can't just willy-nilly pick which reactions you want to go with, right? You got to pick the fuel that you want. So you got to pick one of these that makes a fuel, but you have to balance that out. And I'll explain what I mean by that in a minute. All these reactions here, what we would want to consider as fuel synthesis reactions, right? You want to drive all of these reactions from left to right, right? You want to start from things like CO2, start from the protons in water to make these valuable products. Every single one of these reactions, if you read it left to right, will consume protons and consume electrons. So you need a source of protons and electrons to make this whole scheme go. And that's what this last reaction has to do with this, is that here, we can't, if we drove this left to right, we'd be consuming more protons and electrons. We can't get away with that. We need to produce protons and electrons so that this becomes a balancing reaction where this has to go from right to left. If we oxidize water, we release the protons and electrons that we need to then feed these chemistries up here. Okay, so all of these approaches, the electrochemical and photoelectrochemical approaches, you ultimately need what's called a cathode and an anode. Okay, basically telling you where the reduction is taking place, where the oxidation is taking place. But really, we can think of it as one electrode is doing this stuff, and you need your other electrode to do that. Now the other electrode, it doesn't have to be oxidizing water. You can oxidize other things to release protons and electrons. But usually, you want to pick something that is kind of inexpensive and abundant, right? Like seawater would be a great, or the water that we're all breathing. That's all freely accessible. We can oxidize that. Okay, but you can oxidize something else. You could oxidize methanol and release protons and electrons. But if you're going to oxidize methanol in the first place, why are you trying to make something like methanol on the other side, right? So it's kind of doesn't make much sense. You want to start with something that's kind of inexpensive and abundant. So if this is, but there are other opportunities here. So I just want to mention that. I don't want to say any more about that, but you can pick other reactions here and be clever and try to do some interesting chemistries. But conventionally, this is what a lot of people work on because, again, water is kind of inexpensive and abundant. And what this is really telling us is if you want to know how much energy you're putting into this process, you got to take the delta in voltage between whatever your fuel synthesis reaction is, whichever one of these you pick one of these reactions, figure out where it is on the scale. The delta between that point and that point tells you the minimum voltage that you need to put in to get these reactions to go. Okay? And that's basically the basis for our thermodynamics. Okay. So let's talk about calculating efficiencies based on that number. So let's say we have some, water splitting or CO2 conversion device. We can define our power efficiency as how much power do we get out of this thing in the form of the fuel versus the power that we input in terms of the sun. So one easy way to define it is the rate of chemical energy production per the power input from solar energy. And so this is the expression that we would use, a delta G and say joules per mole of whatever that intrinsic energy content is, multiplied by the rate at which that fuel is being produced, summed over all fuels that are coming out this pipe. Okay, that's going to give us how much chemical energy we're producing in the numerator. In the denominator, it would be, this is, for instance, solar radiation as your power input, and then the insulated area of the device. Alternatively, there's another way to express all of this, is you can express your delta G rather than joules per mole or kilojoules per mole. You can express it as a voltage, like from the previous slide, and then if you multiply voltage by milliamps, which is a rate of reaction, how many milliamps per square centimeter you're making your fuel. If you multiply those two, you get milliwatts, and then you divide by the milliwatt per square centimeter of the solar radiation. That's another way to come up with this expression. Okay, so obviously efficiency will always be an important parameter. This is STF, solar to fuels efficiency. And this is true for any scheme. No matter how you make your fuel, if sunlight is your input, this is how you can define an efficiency. If you want to use solar to hydrogen efficiency as an example, then you just plug in the numbers for hydrogen, which is 237,000 joules per mole and 1.23 volts, and you plug them in and you can get your efficiencies. And of course, an expression like this would insinuate that 100% of your current goes to water splitting instead of some byproduct. Okay, so what did we talk about? We talked about fossil fuels. We talked about pathways to renewable synthetic fuels. Obviously, we motivated by saying, boy, fuels are great. We'd love to make them renewably, sustainably. We talked about some of the thermodynamics that we need to consider and the efficiency involved. Let's start talking about a little bit more about the technology in these domains of electrochemical and photoelectrochemical pathways. And like I said, let's talk about hydrogen first because that's where the technology has developed fastest, and we can leverage that when we talk about extending it to carbon-based fuels. So hydrogen, first and foremost, if you walk away remembering nothing else, remember that we already use an awful lot of hydrogen. In fact, in 2007, we estimated the consumption about 65 billion kilograms that year. And we all know there's 7 billion people on the face of the earth, so that means every man, woman, and child on the face of the earth was responsible on average for 9 kilograms of hydrogen being made, okay, per person. So that just gives you a sense that, boy, if you could make that hydrogen renewably instead of from fossil fuels, you could put a dent into the energy problem. That's how I view numbers of that scale. So it's about a $100 billion industry and already represents about 2 to 3% of global energy consumption just going to hydrogen production. Yes, sir? Is it mostly used in chemical synthesis? Absolutely. What chemicals do you think we're making? It is used in plastics, fertilizer and petroleum. Absolutely. Those are the two biggies. So ammonia synthesis to feed people, right? So we would not be able to sustain 7 billion people on the face of the earth if we relied on the standard nitrogen cycle. The Haber-Bosch process takes the nitrogen that we're breathing right now, the 78% in air, combines it with hydrogen that comes from fossils, usually steam methane reforming, so from natural gas. To make the hydrogen, you put H2 plus N2 and do all that catalysis to then make ammonia, NH3, and of course that's the primary ingredient of fertilizer. So about half of all hydrogen made on Earth is for that purpose, so to feed people. The other half goes to upgrading and refining oil so that we can actually make it more valuable and more usable. So I'd say those are two pretty important areas of modern technology, and that demand is not going away anytime soon. In fact, that's probably going to increase. The number of people on Earth that need to be fed is going to keep increasing, And we're probably going to continue using not just oil, but maybe even heavier forms of oil that require even more hydrogen to treat them, to upgrade them. So like I said, it usually comes from steam methane reforming or coal gasification a little bit, not quite as much as steam methane reforming. And that's pretty cheap because you're just getting this stuff from the ground. It's about $1 a kilogram of hydrogen. If you were to use a coal-fired power plant and electrolyze water instead, it'd be about $4 to $5 a kilogram if you're using cheap electricity. So if you're kind of in the West Virginia part of the world, not in the California part of the world. So hydrogen is already a massively important molecule that we need in the chemical industry, but this could also be a fuel. And I wanted to just give you guys a really quick state of fuel cell cars today on one slide. You know, fuel cells have had a really interesting history. About 20 years ago, nobody was thinking about the energy problem. And then about 15 years ago, you know, around 2000, people started realizing that there might be something going on. And around that time, people said, wow, you know, what are we going to do? And then hydrogen was really kind of coming into the limelight, into the spotlight. And people were saying hydrogen is going to save all of us, right? And hydrogen cars, et cetera. That technology was not ready for prime time. And it took a beating as a result. I mean, that technology was just not ready for that type of discussion. And so a lot of excitement over fuel cells really waned in the period of about 2005 to 2010. Federal government started kind of backing off of it too. Really interesting thing happened. The car companies didn't back off of it. In fact, they kept pushing forward. And all of a sudden the government said, whoa, well, wow, GM is still working on this, and Toyota is still working on this, and Honda is still working on this. And where are we today? Now there's been over 3 million miles driven on hydrogen fuel cell cars, over 27,000 refuelings. Basically, you know, almost every major manufacturer is putting out these cars. Hyundai just announced that there's 500 Santa Fe's on hydrogen fuel cells that are being leased now in California. And Toyota just announced that the very first commercial fuel cell vehicle goes on sale in California in 2015. So here it is. Now you can actually buy a fuel cell car, which you couldn't say that even a year ago. It's going to be about $65,000, which of course isn't cheap. But these things get range of 300, 400 miles. They fill up in about 5 minutes. Sounds like a gasoline-powered car. And the hydrogen distribution network in California is actually quite good, which is exactly why the car manufacturers have really been investing in California for their fuel cell vehicles, especially in the Los Angeles area, but in the Bay Area as well. So, you know, we'll see where this goes, but I have to say it's extremely promising. I already see, question over here and then over here. Yes, ma'am. We'll start with you.
What's the benefit if you're going to take natural gas to make the hydrogen and then feed it in at a lower power density to a car? Why?
Right. So great question. So California had done a study. I don't have the slide on me handy. California did do a study that showed that, I mean, because natural gas is a cleaner fossil fuel than the other fossil fuels, because of the fact that, and because hydrogen has so much energy density, and because fuel cells are so much more efficient than internal combustion engines, that when you add all of this up, the actual impact of a fuel cell vehicle, even if it's coming from natural gas to begin with, is actually less than your typical conventional internal combustion engine car. However, that is not how we want to do things in the long term in the future. It'd be much better to make hydrogen from renewables, from water and from sunlight, than it is to make it from natural gas. But the good news is that, as we all know, especially in this country, we got plenty of natural gas, and that's rising. And so doing anything productive with natural gas right now is a good thing, and it's very inexpensive. And so this is a pretty reasonable way to go. And I also want to remind everybody that I'm not saying that we should put our chips in any one basket. So this is one piece of the puzzle. I'm not saying this is better than a battery car. I'm not saying that it's better than an internal combustion engine car. It's just a different technology that is kind of intrinsically going to be, it's already going to be more sustainable on day one than conventional fossil fuels, and has a future that looks even brighter as time goes on as we come up with sustainable ways of making hydrogen. Also, it's very important to point out that fuel cells can deliver a lot more power. They can deliver plenty of power for large vessels, so like shipping vessels, and have the range too. So, you can have large range and plenty of power for big trucks, shipping vessels across the Pacific. Those are areas where batteries are going to have a much more challenging market. So, hey, if you're commuting and you're only commuting 10 miles each way or less, then battery cars are fantastic. If you can afford the kind of car that can get you 300 miles, fantastic, right? So it's just a different technology. It's a complementary technology is how I would put it. So the point of my slide here is really to say that hydrogen vehicles are really moving fast, and they're actually in the market. They're going to be sold, and time will tell how the market responds to all of this. But I just wanted to point, I mean, really I wanted to say that if you can make hydrogen sustainably, there's a market that's coming to use it. Yes, sir?
What has been the basic problem with fuel cells? It seems they're a little like fusion that you know, they've been talking about that that's a great technology for 20 years and always will be. Is it cost? Is it reliability? Is it safety?
So the first thing I would say, it is nothing like fusion, because cold fusion hasn't even been shown, if you were to ask me. Whereas fuel cells definitely could work 20, 30 years ago. I mean, the technology worked. It just wasn't. It didn't last very long. It died quickly. It didn't have high performance. It didn't generate enough voltage, enough current, and it was really expensive. And so for all those reasons. And so what people have been really working on, especially in the car companies, is pushing that technology to A, last longer, B, provide as much power as possible with smaller devices, C, get rid of precious metals, because precious metals are obviously costly. So your typical fuel cell car, a car like this one, in fact, I don't know if they've, I have heard, I don't know if they've publicly announced exactly how much platinum is inside that fuel cell, but the numbers I've heard are as low as 30 grams, and the highest number is 50 grams, 30 to 50 grams of platinum. A gram of platinum costs about $50. Okay, so you do some mental math, that's like $1,500 to $2,500 worth of platinum in your fuel cell car, which might sound like a lot, but it's actually not too bad. It's not too bad. It used to be an order of magnitude more than that when it was $10,000 worth of platinum or $20,000, then you can see why it was so expensive. But if you compare it to a battery in a Tesla, for instance, how much does the battery pack in a Tesla cost? I mean, that's tens of thousands of dollars, right? So $1,500 for platinum or $2,500 for platinum is not so bad. Then you might say, what about scalability? How many fuel cell cars can you put out on the road? And I would say 50 grams is still too much. I'll tell you what's a much better number is 5 grams. If you can improve the catalyst in a fuel cell, so you could reduce the amount of platinum by 1 order of magnitude to go from 50 grams to 5 grams, guess what? 5 grams is identical to how much precious metal we all have in the catalytic converters in our current cars. And we know that that's a scalable technology. So if you can get down to that 5 to 10 grams per fuel cell car, and a fuel cell car doesn't require a catalytic converter. It's got nothing coming out the tailpipe that it needs to convert. It's water. So then you can say that becomes instantly scalable. So that's kind of the challenge, and that's another area of research that we work in my lab is how do you get that order of magnitude improvement per gram of platinum in activity, and if you can do that, then you're in a good place. Yes, sir.
Are there any safety issues with this? Because earlier you mentioned, a car, you got so much energy density, it's like you're driving a bomb, but it's practically stable. Now, hydrogen fuel cells is going to be the same, or is that an issue?
So any combustible, any flammable material will always have safety hazards. The question is, can you engineer solutions to address that? And so again, 3 million miles driven, and they've engineered them to be pretty safe. One thing I will say that is intrinsically quite safe about hydrogen is that if the gas tank ever gets punctured, the gas tank, right, the hydrogen tank gets punctured, that hydrogen is so light, it's just like this vertical pipeline to outer space. Right? Whereas if you puncture a gasoline-powered car or diesel, like all the fumes and all that liquid is just going to linger around. So there's actually a lot of safety reasons that actually it could be even better. But nevertheless, you have to engineer it appropriately. It's just a different engineering problem. So really, this slide is just to show that as of October 2014, fuel cells are looking pretty good, and I think it's going to continue to get even better. So now let's talk about making hydrogen sustainably. So now, is this pie in the sky chemistry, being able to make hydrogen sustainably? Yeah, you can make hydrogen from natural gas. But take a look at this. These are all devices that I won't get into the nitty-gritty details right now, and not even later in the talk, because there's a lot to be said about these things. We'll talk about some of the processes involved, but these are just 3 different devices that I just plucked out to show you today that you can make hydrogen. Here, 18% solar to hydrogen efficiency. 12% solar to hydrogen efficiency, 10% solar to hydrogen efficiency. These efficiencies look pretty similar to what you'll see in commercial solar cells, right? Solar cells on people's roof are kind of, in that ballpark range. Are they as efficient? No, of course not. It's a lot harder to take it, to do everything you're asking a PV to do, and then to go, oxidize water and generate hydrogen as well. It's much more, you're asking these devices to do a lot more than a PV would, but you're making a chemical directly with no issue with storage. You can store that hydrogen, piece of cake, compared to storing electricity. Storing electricity is way harder of a problem. So you're getting a more storable form of electricity. I also want to point out that these numbers are based on the delta G of hydrogen, the intrinsic energy content of delta G. And to be fair, some other technology, and that's the most conservative number you can go with. If you use like the lower heating value delta H or the higher heating value delta H, these numbers only look better. So I just want to, for those of you who know your thermodynamics, I know some of you are in the audience, that's kind of important consideration. So point is, these are not pie in the sky devices. These have actually been developed by people who work on these technologies in the lab. And I want to show you this video from my buddy Todd Deutsch, who's over at the National Renewable Energy Lab. Oops. Let me try that one more time. So this video will give you a sense of how this works. So here's a real photoelectrode that he's illuminating. And these are the bubbles, these are hydrogen bubbles coming off. So he's just shining light onto this photoelectrode, which is, the light comes in, you're exciting electrons in holes, and those electrons are going into water to make H2, and the oxygen is coming off of that counter electrode. And Todd is kind enough to turn on the lights and show us that he doesn't have like a 9-volt battery in the back doing the chemistry. He's just shorted the two electrodes, one of which is the anode and the other is the cathode that I was describing earlier. And then he also wants to prove to us that he's not just doing it with some like super powered lamp. He can actually take this outside in Colorado, in Golden, Colorado, and show that just the regular sun in Colorado can do this too.
Can you concentrate solar light and drive that faster?
You absolutely can, no question about it. And I'll show you that there actually is good reasons why one might want to do such a thing. Okay, so that's kind of a real demonstration. All right, so now, great. So this is not pie in the sky chemistry. We can actually make these materials. We can make these devices. They actually do work in the lab, but nobody's ever built, a huge facility to actually make hydrogen industrially by this process. How much would that cost, right? Tough to know until you actually build it. But you can definitely do some analysis to give you a sense of how much it would cost before you go about building a plant. In fact, that's how every company in the world works, right? I mean, you always estimate the cost before you build anything. So here's the question. How much might it cost to make that hydrogen if it's produced by this large-scale photoelectrochemical water splitting? So in this techno-economic analysis, how do you conduct a techno-economic analysis? So this is how we go about doing such a thing. The first thing we do is we basically, without even having that perfect material or good material, because this is really a materials problem is what it comes down to it. While people have made devices that are 18% efficient and 12% efficient, et cetera, they have other issues. They're really expensive. They're not very durable, right? It's kind of like the story with fuel cells, where fuel cells were 15, 20 years ago. They just weren't ready for prime time, okay? And we're still not quite ready for prime time yet on these, but they're getting a lot better. So what we can do is, even without having that material under our nose, we can still define, let's hypothesize, right? I've got some students in my lab right now who are working on this. What if tomorrow morning one of them develops, a material and eureka, I've hit all my targets for efficiency and stability and cost, right? How much would it cost to build a plant based on that material? We can do that analysis without even having the material with us. So we can just kind of define some performance ranges. We can then brainstorm what the reactor looks like. So this is like chemical engineering plant design 101, where you basically design your reactor, design your chemical plant around it. Okay, so we basically thought of a bunch of different types of reactors. We down selected which we thought were most promising based on cost and performance. Then you go about designing all the auxiliary systems in the plants, right? All the pumps, all the pipes, all the compressors, all that other stuff that you need to make this plant work. Once you have everything that the plant consists of, you can develop a bill of materials and capital costs. And then you can figure out, using some tools that the Department of Energy has created, how to figure out how much does that hydrogen cost per kilogram that you make. Okay, so we go through that whole exercise. You can actually get how many dollars per kilo it would cost. And the nice thing is then you can go back and do some sensitivity analysis. You can go back to your original assumptions on how well that material performs and say, well, what if the material cost twice as much? What if it was twice as efficient? What if it lasts half as long? How would that impact the price of hydrogen coming out the plant gate? Okay, so let me lead you through that exercise. So This is what we came up with, really 4 different types of reactors. I'm going to call them type 1, type 2, type 3, type 4. And this is just to give you a sense that not only did we design what the reactor looks like, we designed the entire chemical plant. And let me show you in more details how this works out. So type 1 is what we call the colloidal suspension reactor. So you have a suspended catalyst material, photocatalyst material. So this is like a semiconductor that has different catalysts decorating the surface. And we put these in bags. These bags are huge. These bags, you can see, they're 300 meters long by about 12 meters wide, but only about 10 centimeters tall. So it's just a small amount of liquid water. This catalyst is floating in here. The sun shines. It takes that water, takes that sunlight, excites electrons in holes, makes hydrogen and O2. The bag inflates. And then you have all this wiring and piping to basically get that hydrogen and oxygen out. You got to separate it from the water as well, process it, compress it, voila, you can sell it out the plant gate. Okay, so now one thing about this is about as cheap as a design as you can possibly think of, but you're making hydrogen and oxygen in the same gas space, and that could be dangerous. Absolutely. Reactor type 2 deals with the issue of hydrogen and oxygen being in the same headspace. Here you've got now multiple baggies that are linked through what we call ion bridges. And now you can have 2 different types of photocatalysts, one that's dedicated to making hydrogen in this compartment, one that's dedicated to making oxygen in this compartment, and you have some ion that kind of floats back and forth and kind of balances the equations for you. And the nice thing is that then this one is only inflated with H2, this one's only inflated with O2, and then of course you pull these things out and you still have some separation, some compression processes, etc., sell your hydrogen out the plant gate. This is definitely going to be more expensive from a manufacturing point of view, but you've dealt with separations up front, which is helpful. Reactor type 3 looks just like a photovoltaic that's dunked underwater. So you all have seen photovoltaics that look pretty much just like this. But now we're feeding in water on one side of that photoelectrode, you're making hydrogen. On the other side, you're making oxygen, so you have natural separation of the 2 products. Pull it out, again, compression, separations, sell your hydrogen. And then you can imagine that same type of contraption where you use some solar concentration, just like you were asking. So we did some analysis on, this is 10x concentration, so not 10,000x or 1,000x, but some modest concentration. The nice thing is that so basically you're paying for the mirror. So if this material turns out to be really expensive, you can make that module smaller and then just pay for the mirror instead and capture the same number of photons. All right, so these are the 4 different types of reactors. How much did the hydrogen cost based on these assumptions? Our target here from DOE is about $2 to $4 per gallon of gasoline equivalent, GGE. This is the way the DOE wants to just put everything on a level playing field. It doesn't matter if you're working on butanol or ethanol or hydrogen, you can turn it into gallons of gasoline equivalent. The nice thing is with hydrogen is that 1 kilogram of H2 is equivalent almost exactly to 1 gallon of gasoline in intrinsic energy content. Okay? So these are the numbers. $1.60, $3.20, $10.40, $4. Okay, so clearly the price is very sensitive to the type of reactor you chose to begin with. That's an important result. That's that's why chemical engineers are important, because you can actually design things and build large-scale systems and figure out what the costs are before you go about building it, so it can help guide you in all of this. This turned out to be really cheap. The only problem with this is that this is based on an assumption of 10% efficiency, and 10% is not, I showed you some devices that can operate at 10% and higher, but no one's ever made this type of system anywhere close to 10%. The ones that hit 10% look more like this. Okay? So basically, these are way cheaper, they're low cost, but the lab demonstrations are nowhere close to even the 5 or 10%. Whereas here, people have certainly made 10 to 15% devices, but then these are just intrinsically more expensive because they're just more expensive to process, to fabricate these types of modules. But nevertheless, they're all in the right order of magnitude, right? They're all within, they're all kind of in the ballpark. But the game doesn't end here, because we made some assumptions on performance here just to get an idea. And like I said, we could perform some sensitivity analysis on this. So take that type 4 reactor, the one with the solar concentrator. Our base case assumptions were 15% efficient. It cost $316 per square meter to make, and it lasts for 10 years. That's where you get the $4 from. If you improve the efficiency to 25% from 15%, the cost goes down to $290. If you lower to 10%, it jumps to $560. The cost, we said $316 was the base case. If you made it $200 per square meter, again, you can go from $4 down to $370. If it becomes more expensive panel, of course, it becomes more expensive there. Oops. And then lifetime, 10 years was our base case. If it lasts for 20 years instead, of course, it gets cheaper. If it lasts for only 5 years, it gets more expensive. So this is kind of the sensitivity to each of these three factors. And of course, if you, the question is, if you did all three of these things, you made it more efficient and you made it cheaper and you improved the lifetime, then of course the cost could go even further below $2.90. Okay, so this is saying that we're in the right range of this $2 to $4 that DOE is calling for. Yes?
What would be a reference for distribution and final compression?
Great question. So, I'm told by DOE that we can expect that to be $1.50, about $1.50 a kilo, right? So if you're making your hydrogen at $2 a kilo, then it would cost actually $3.50, at the pump, and which is what we're paying already for a gallon of gasoline. But remember, a fuel cell vehicle gets you a lot more mileage because it's a lot more efficient than an internal combustion engine. So a typical fuel cell vehicle, like the one I just showed you, that one gives you around, I think it was 350 miles on 5 kilograms of hydrogen, right? So it's about like 50 miles per gallon, if you will.
It sounded like you were just comparing the cost here to the price at the pump, which includes profit and taxes and other stuff.
Right. So the price of the pump that we're paying here in California, it's about 50 cents, I think. Anyone here knows can correct me. I think it's about 50 cents of taxes is what we pay. So gas is about $3.50 right now a gallon, and so $3 of that is, if you want to call it, the intrinsic cost of producing it and distributing it, and then the other 50 cents goes to the government.
And profit is in that?
And the profit, anyone here who has knowledge, I'd love to hear it, but my understanding is its profits are on the order of 5 to 10 cents per gallon is a typical value. So, companies don't typically make their money off the fuels. Remember, fuels is a massive market. It's so huge that even if you're only making a nickel per gallon, you're making a lot of money, right? Those oil refineries are cranking out 150,000 barrels a day. Okay. Yes.
But you might be able to get carbon, low carbon fuel.
Absolutely.
On that, which would be what, 50 cents, maybe 75.
Yeah, I mean, so think of it this way. I mean, if you want to drive, here's one way to put these numbers in perspective. I mean, even without taxes and stuff like that, carbon tax incentives, even if we avoided all of that, if I paid for, let's say it was $5 a kilo at the pump, on 5 kilograms, I can drive my car, about, let's say, 300 miles or so. 300 miles on $25. Right? Can you do that? I mean, right now it's at $3.50 a gallon, so I'm just doing this mental math in my head. You were asking, so that's like 7 gallons of gas. Can you go 300 miles on 7 gallons of gas in a typical car? And most cars can't, right? So even if you're paying $5 per kilo at the pump, and if you're using a fuel cell car, it's probably going to be economically advantageous for you without any subsidies, right? So that's why these targets are so critical. That's exactly how DOE comes up with targets like this. Because this target is not the target that says we have to hit this for this to become useful. This is the target that if you can hit this, it's massive widespread adoption, and you don't need any politician to pass any bill. You don't need any support from anyone. People will say, oh, this is cheaper, I'm going to buy this. Right? And as somebody who works in technology, that's kind of the angle I take, right? If we can make the technology that good, if it's cleaner, cheaper, higher performance, you don't have to convince a soul. My attitude. All right, so the numbers look pretty decent. So the question is, can you make these photoelectrodes that actually can they actually perform this well? Let me get a little bit into the physics, okay? So I know not everyone is into the physics side of this, but some of you I'm sure are. And so let me just say a few words on this, and we'll zoom back out into some big picture concepts in a moment. This is what we call an electronic band structure of a semiconductor. This is if you shine light onto a semiconductor, the idea is you got to excite an electron from the valence band into the conduction band. These electrons, then you got to pull them out, and these electrons are the ones that make your hydrogen. The positive charges left behind are the ones that oxidize water to make your O2. And so this type of this type of process, again, very similar to a photovoltaic. So if you guys go watch, the solar energy and the solar cells lectures, they're going to talk about exactly those types of processes, how the sunlight factors into all of this. The difference is that they're not doing any of this type of chemistry. They're just making current and voltage. So you got to get as much energy out of these electrons and holes. You also have to have good catalysts that can drive these types of chemical transformations at the surface. I'll skip through some of these other issues. You can do some calculations. Okay, let's zoom back out again for a moment. You can do some calculations of how efficient can I expect my solar to hydrogen process to be as a function of the band gap of my semiconductor. The band gap is, the difference between that valence and conduction band I was talking about before. The optical limit says is that, boy, if you get a small band gap, you can get a really high efficient device, like upwards of 30%. But in reality, there's actually a lot of losses in this process, which basically means that you're going to have to use a lot more voltage for other things. And the bottom line is, you can't just keep shrinking the band gap and getting higher efficiency. So we have to deal with this. So I'm just want to tell you about some modeling work that my student Lindsay had led in the group to figure out just how efficient these types of devices can be. Okay, and that's what I want to relay to you today, is how efficient can this be? And she put in a lot of things into this model, a lot of the physics, all the important physics and chemistry that happens in these materials were put into these models. She basically defined, do you have a single absorber, or do you have a dual absorber of two different semiconductors, one on top of the other? Do you stick your semiconductors side by side? She modeled all these losses in the physics and the chemistry of this. She calculated what the solar to hydrogen efficiency would look like, and from that she could identify, well, how do I optimize the band gaps of my semiconductors so I can get the maximum efficiency, or what engineering solutions can I employ to get the most juice out of all of this? So I don't want to go into all the details of how she did her modeling, but at least I want to mention that, so she looked at these different configurations. These are the three main losses that she looked at. Is number one, when you excite your electron from the valence to the conduction band, you don't get all that voltage. You get something less than that. So that's what's known as the open circuit voltage of your material. So she said, okay, how good can that be? How good are your catalysts? And do you have a shunting problem? Shunts are basically when current goes the wrong way. So she puts all this into the model. And now she calculates this as, a maximum solar to hydrogen efficiency if you have a single band gap of a semiconductor. Okay? Very different from the plot before, which kept climbing and climbing and climbing. Now you actually see this peak. And it peaks out here right around 11% or so, with the band gap of about 2.3 electron volts. This kind of sets the target as to what would be a good choice. Now when Lindsay did this, she did this with a very important assumption. She actually used the current state of materials research today. So if you can improve we, as a technological society, if we can make better semiconductors and better catalysts, then this effectively can get higher and higher. And so she explored that with different catalysts and said, oh, wow, there's a sensitivity. If you choose really great catalysts like platinum and ruthenium oxide, that's what it looks like here in black. If you choose catalysts that are less good, then you're going to get lower and lower possible efficiencies. So she did all this type of analysis for a single absorber bandgap case. She also did this for a dual absorber bandgap case when you have two different semiconductors employed, which you can do in different ways. I won't get into the details there. But what I really want to point out is that her calculations show that based on the current state of materials research today, in principle, we should be able to reach 23% solar to hydrogen efficiency if you can make your materials to the best of technological society's abilities today. And that's a pretty good number, if you can hit that. And it's a very realistic number in terms of how good this technology can get. Again, based on how good we are at engineering materials right now, if we get even better, then this number could go 25, 30%, maybe even higher than that. So the point is, I want to bring with all of this, these calculations, this modeling really shows that it is possible to make these devices that are on the order of 20% efficient. And remember all those techno-economic modeling I was showing you, 25% efficient was kind of, if you can hit 25%, the costs start looking very good. This shows you that you can get really close based on where we're at today and maybe even go beyond that. So having said all this, what does this contraption even look like? So here's one way you can think about it. So on the previous slide, I basically showed that the maximum with one semiconductor was about 11%. If you have two semiconductors, you can get 23%. So two semiconductors is better. And here is, if you guys want to take a look at a website that can help get you guys up to speed on these types of chemistries, there is a hub, a DOE energy hub called the Joint Center for Artificial Photosynthesis that I'm part of. And they've come up with a contraption like this. You can read a lot about it here on as to how it works, but there is a question. I want to go ahead and field that. Sure.
The fluorescent slides.
Sure.
What kind of material does she use for 1.2?
Right. So that's where the problem lies. So here, for instance, if you picked silicon is 1.1 eV. So that in principle is pretty good. But then no one's ever developed a 1.8 EV band gap that could be silicon's counterpart. But people have made semiconductors that work as well as we need them to, but just not with that right band gap, if that makes any sense. So that's why nobody's ever hit 23% in the lab, is because nobody's made that material. But if we could make a material with that band gap and make it as well as we've made other good semiconductors, then you should be able to hit 23%. That's what this modeling is trying to say. Yes?
CGS or CIS, right about 1.8?
We are working on exactly that material. Exactly. So there's really a lot of interesting phase space, SIGS-ish type materials, copper gallium selenide. If you sulfur dope it, if you change indium to gallium ratios, there's just a lot of things you can do with that material to tweak its band structure. Any other questions? So yeah, so that's a big part of this whole research, is how do you engineer the band gaps of semiconductors. So now that we're looking at the innards of what a device might look like, you can think of having some micro wires of semiconductors going up, some micro wires of semiconductors going down. They're sandwiched with some membrane that allows protons to go through, because remember, on one side you're catalyzing oxygen evolution, which releases those protons and electrons. You need those protons and electrons to go through to the other side, but you want a barrier to prevent hydrogen and oxygen molecules from mixing. So you want the hydrogen to go through, the protons I should say to go through, so then you can make H2 on the other side, or stick those protons and electrons onto CO2 to make fuels and chemicals, right? So there's basically all these materials needs. You need catalysts for oxygen, catalysts for hydrogen, catalysts for CO2 reduction. You need semiconductors as a photoanode, semiconductors as a photocathode. You need a membrane to unify all this, and it all has to work together under the same operating conditions. And that's really what the Solar Fuels Hub is trying to do within one center, though there's a lot of researchers in the world, including myself, which we have our research labs where I have students who are kind of working all on different elements of this device, of this type of design. So for this very last part of, we're approaching the end here. I probably have like 6 more slides to really talk about catalysts, because of course catalysts are going to be key for all these chemical transformations. And these are the 3 metrics by which we view catalysts, right? We want them to be active, meaning efficient. We want them to be stable, last for a long time. And we want them to be selective, meaning they can make exactly the product we want and not the products that we don't want. So if I were to ask you, which of these is most critically needed in catalyst development, what would you guys say? Yeah, you need all 3 for sure. But basically, it really depends on the reaction as to what's the pressing need. What's the big challenge? What's the big problem? And so here on one slide, and by the way, these slides have been uploaded as a PDF, so you guys have access to all of this. Here is my summary, Tom's summary of electrocatalyst development for making hydrogen, making oxygen, and converting carbon dioxide into fuels and chemicals. And so hydrogen, so these things are ordered in terms of hard, harder, and hardest. Let's talk about hydrogen. If you want to make hydrogen, the good news is that precious metals basically meet all the performance metrics that we could hope for. So that's good. We have catalysts that actually work. They're stable, they're active, but they're costly. And there's the scarcity issue, right? So maybe they're not quite scalable, but at least we can use them to start getting this technology off the ground. I don't know if putting platinum in such a device would be able to scale to the 5 terawatt level, but it can certainly scale to the 5 megawatt and the 5 gigawatt scale, right? So to get to 5 terawatts, you got to go through megawatts and gigawatts. So I think that's a reasonable, at least we have something that we can use that's quite good. There are non-precious metal catalysts that are pretty good too. They're not quite as active, but they might still be feasible. Some are only stable in near neutral or base, like nickel molybdenum alloys are pretty good under those conditions. If you're working in acid, there are metal phosphides and sulfides like MOS2 that are quite good. And selectivity is actually not a problem at all for hydrogen catalysts. If we go back to here, so from a selectivity point of view, hydrogen has no problem. There's plenty of catalysts that are stable. If your precious metal activity is phenomenal, if your non-precious metal is still pretty good, it really just comes down to, if you go with the non-precious metals, you're going to take a hit in efficiency. Is it worth it? And if you go with precious metals, is it scalable enough? But by and large, we're doing okay in this domain as a community. Oxygen is harder, as I mentioned, a lot harder, in fact. In fact, it's so hard that you could go with the most expensive catalyst known to humankind, and it still wouldn't be quite good. It'd be a lot of room for improvement. So you'd be basically throwing away about 0.3, maybe 0.4 volts, okay? Which is precious. Those are precious volts. We don't want to lose any. So the bad news is that there's improvement. There's large improvement for activity. If you want to call it good news, there's some non-precious metal catalysts that are as good or better than the precious metals, but they only work in base or near neutral. If you work in acid, there's nowhere to go other than precious metals. Theory has also explained why achieving the desired activity is so challenging, so that's helpful. It gives us some guidance there. And there are some commercialized electrodes in industrial electrolysis. Actually, it's very important. I didn't make this point earlier, but these types of schemes of making fuels from sunlight or fuels through these electrochemical processes, it's important for everyone to know that there are already, here today in the modern chemical industry, absolutely massive industrial processes that work on electrochemical transformations. The two big ones being electrowinning of aluminum, so going from aluminum ore to aluminum metal, so for our Coke cans, etc. Okay, so that aluminum that's an electrochemical process that produces almost all of that aluminum. The other major process is chloralkali, which is a process by which we make chlorine and sodium hydroxide. You take brine, you take in salt water, and you electrolyze it, and you make NaOH and Cl2. And both of those compounds, okay, each one is on the order of 50 billion kilograms a year. So it's similar to hydrogen, meaning that, again, every man, woman, and child on Earth is responsible in that case for 7 or 8 kilos of each of those being made. Okay, so these are already terrestrial processes. So, the idea of making hydrogen or CO2 conversion products using electrochemical technologies or photoelectrochemical is really not, it's not that far from reality in that context of scaling up. So those things exist in industrial electrolysis, which is good news. If you're going to use seawater electrolysis, though, unfortunately, a lot of catalysts will favor making chlorine and bromine instead of oxygen, which is actually great if you want to sell it, because these are more valuable than O2. But it also means it's a problem in terms of the corrosive nature of these species. They might corrode your instrument. And then finally, if you want to convert CO2 into fuels and chemicals, like I said, this is the most challenging by far of the 3 reactions. There is a lack of viable candidate catalysts. Like, we really don't have anything. I've yet to see any catalyst ever developed that I think really has significant commercial potential. That could change. But that's kind of where the state of the field is for that, which is why we started everything with hydrogen and talked about the technology development in terms of hydrogen, because if you can come up with CO2 catalysts that work just as well as the hydrogen catalyst, but then you're going from CO2 to propanol, right, or CO2 to gasoline, right, then you're really in business. Okay, so it's all about catalyst development here. If you're going to convert CO2 into anything, it's much easier to make small molecules like formate or carbon monoxide than it is to make hydrocarbons or alcohols. Copper can make a lot of these different chemistries. That we talked about that yesterday in the technical sessions. But really, the bottom line here with CO2 is that there's a lot of work that's needed to make those processes feasible. But if you can make good catalysts for CO2 conversion that are as good as hydrogen, like I said, you're in good business. This is a technical data slide that I thought might be interesting to summarize where the state of the field is for hydrogen and oxygen catalysts. So this is like data to prove the points I was making on the previous slide. There's a very complicated plot with about 60 different catalysts that have been benchmarked. So part of what I do is part of the Joint Center for Artificial Photosynthesis is I work in the benchmarking team where we're really trying to make apples to apples comparisons on different catalysts. And what this plot is trying to show you is It's really a measure of catalyst activity and stability. And it's showing hydrogen catalyst. This HER means hydrogen evolution reaction. So this is the plot for hydrogen catalyst in acid, hydrogen catalyst in base. Here's oxygen evolution reaction in acid, oxygen evolution reaction in base. And what you're looking at here is this is a plot for every one of these quadrants. It's showing you how much voltage do you need to put in to get you 10 milliamps per square centimeter of current. And so, if you plug that 10 milliamps per square centimeter of current into those equations I mentioned for efficiency, that basically gives you a solar to hydrogen efficiency of about 10%. Okay, so for a 10% device that you would deploy, you need to run about 10 milliamps per square centimeter current. So the x-axis data point tells you where that is at times t equals 0. The y-axis data point tells you where it is after we run it for 2 hours continuously. So if you're right on the line, that means you're a perfectly stable catalyst. If you're off the line north of it, that means you're losing activity with time because you need more voltage to get there. If you're below the line, it actually means that you got better with time. But sadly, not many catalysts do that, right? They usually get worse. They don't get better. But it does happen in some cases. So what this is meaning to say is that, wow, there's a lot of good catalysts in acid and in base for hydrogen that operate near zero. This is where you want to operate. You want to say, these are catalysts. The closer you are to zero, that means the less energy penalty you're paying to get that current. So the best catalysts are close to zero, and for hydrogen, in acid or in base, either way, you got some decent options, even ones that are non-precious metals. For oxygen, you can see, boy, there's just nothing going on anywhere near zero. That's what I mean. It's a much harder reaction to catalyze. If you look in acid, the big deal is that the only ones that are even reasonably close there are precious metals, ruthenium and iridium. And if you go to non-precious metals, then in base, there's a lot of non-precious metals that are just as good as ruthenium and iridium, basically. And so that's what I was saying. For catalyzing oxygen evolution in base, you don't need a precious metal, but there's a lot of room for improvement to get closer to zero. So that's the big challenge for oxygen. I won't go into this data. This is a distillation of all the data I just showed you on the other slide, and we don't need to harp on that any further. For CO2, we already looked at these reactions. These are the ones that we want to catalyze. Why is CO2 so much harder than hydrogen? And the answer is there's a lot more steps involved. And so CO2 to methane, for instance, requires 8 steps. So CO2 comes down, hit it with a proton electron, hit it again, hit it again, hit it again, hit it again, again. Finally you've made your methane, you've cleared water off your surface, you can finally go back to square one. This process is a piece of cake. There's only 2 steps. You want to make methane from CO2, that's 8 steps. And if you want to make things like ethanol, it would be like 12 steps. And the bigger the chain gets, the more steps, the more you're asking your catalyst to do. And that's really the challenge in CO2 chemistry, is that how do you make a catalyst that does every one of these steps just right? That's the fundamental problem. Not many catalysts can do anything like that. One of them that can, to some degree, is copper. And I showed this slide yesterday in the technical talk. Basically, copper can make a whole host of very interesting products. It can make things like methane and methanol. It can make all these C2s, ethylene, ethanol, acetate, ethylene glycol. It can make even a bunch of C3s. It can make propanol, allyl alcohol, acetone. It can make a lot of these products. But there's 2 major problems with copper. Number one, you really have to dial the potential really negative to get these chemistries to go. So you're taking a hit on the efficiency of the process. The other problem is that you're pretty much making them all around the same time, meaning you're just making this big mix of products that then you'd have to separate. And guess what? It takes energy to separate molecules. And so this is not commercializable in my opinion. But the fact that it can actually make these products is what's really interesting. And so that's really the frontiers right now, is trying to understand, if this is my opinion, the frontier of research in CO2 conversion in this way is trying to understand what makes copper tick, what makes other catalysts tick, what are the governing factors at play. The better we understand that, the better we are primed to make a good catalyst. And so I didn't go into any of the details on I think yesterday in the technical session, and for those of you who are watching on video, GCEP is putting those presentations online. for everything we talked about in the technical session yesterday, that is state of the art in the field of CO2 catalysis. So I would encourage you, based on this kind of thinking, if you want to go back and look at that, that would be helpful. So this is the last slide. And let me just leave you with some take-home messages in this area of synthetic fuels. I think this first bullet point, I think we can all agree that chemical fuels are a magnificent form of energy storage. That's a big reason why we use hydrocarbons today. And researchers in this area of solar fuels were aiming to develop a way to produce fossil fuel-like molecules, but using water, carbon dioxide, and solar energy, right? Renewable resources, sustainable resources. Technologically, this can already be done. I mean, I just showed you copper is not a perfect catalyst, but you can make hydrocarbons, you can make alcohols with copper. We have semiconductors that can absorb sunlight and make electricity to drive that process. We do have catalysts to make oxygen from water. We have all the technology. It's just not good enough to make it cheap enough to make it worth scaling up. But the good news is that a techno-economic analysis shows that, at least for the case of hydrogen, it is possible to reach a good techno-economic parity with fossil fuels if you can make materials with the appropriate properties. So that's really what's driving research in this area. And the bottom line is that that's the incentive for us to keep pushing in the R&D world. Because if we can make the right materials, if we can make the materials with the appropriate properties, then we can start building commercial opportunities. Okay. So any questions? Yes, sir. Absolutely not. I mean, it's a wonderful idea. I mean, every idea is on the table. Every idea is on the table. I mean, which renewable resource do you want to use? Do you want to use sunlight? Do you want to use wind? Do you want to use geothermal? Do you want to use a biological? Do you want to take an organism that is a methanogen that knows how to do all kinds of interesting chemistries with these types of C1 species? You feed it formate, you can get methane out, or feed it CO and hydrogen, it'll spit something else out. Absolutely, you can. So, or just use the absorber, right? So you could imagine building a solar capture device based on those types of antennas. Sure, I mean, people are doing that sort of thing. The question is, can you make it efficient enough, stable enough, cost effective, right? Those are the challenges. I mean, technologically, I think a lot of people have worked on these types of concepts. I mean, biomimicry is a huge, it's interesting. On one extreme, you have using the biology itself, which a lot of people do. They actually use the bugs and engineer their metabolisms, right? The other extreme is you stay as far from biology as possible, and you make just things that are rocks, right? Like purely inorganic copper and things like that. But there's this wonderful phase space in between, where you can either take principles of biology to make a rock that emulates what the biology does, or you can make maybe a molecular species that you synthesize as an inorganic chemist might in their lab that has some of the design principles from the biological catalyst, but it's still a man-made thing. Or you can imagine hybridizing things. So we could imagine, using a photoelectrode like I just described, that you can go, you stick it in water, you shine light, and you go from CO2 to formate, and then a bug grabs that formate and spits out butanol. And in fact, that has been technologically shown as well. So there's just so many different ways of hybridizing and coupling and mimicking. There's a lot of room to roam there. And you can think of it as an overall process, or you can think of it as, I'm trying to do this one thing better. What could I learn from biology or use from biology to make that happen? You want to make hydrogen? What if you plucked out the hydrogenase enzyme out of a species and put that on a surface and drove hydrogen evolution that way? And that's been technologically shown too. So yeah, a lot has been done and shown technologically, but I don't think we understand it well enough to really engineer the system that's ultimately going to hit those cost targets. But there is a path, and that's the important thing. Yes, sir.
There was something you said earlier that I'm not sure if I understood. You gave the example of, say we put 7 kilograms of hydrogen in a car and went 300-400 miles. And could you really do that on 7 gallons of gas? Not so much.
You could.
You've got a great gas mileage car.
Sure, like a Prius or something like that, right?
And so that made it sound like that $2 to $4 target is a little bit punishing.
Punishing in that it's too steep of a.
It's too low.
Yeah. So
like you can have a little higher target and still hit a pretty good look.
So that's exactly what I meant by DOE is setting like the ultimate target. It's like once you hit that target,
okay, thank you.
The world will be in the palm of your hand, right? But there are plenty of opportunities to make technologies that can make a big impact and make you money, even without reaching that target, is the way I would put it.
Another way to look at it is if you're driving a $70,000 hydrogen car, is $7 a gallon for hydrogen all that expensive?
Like I said, even $7 for a kilo of hydrogen, I mean, that basically will give you the mileage of $3.50 gasoline anyway. And if it's produced renewably and sustainably, then it's even, can make you feel good at the same time as opposed to being a fossil fuel. That's absolutely correct. In fact, by the way, if you lease any vehicles, there's a lot of leases for fuel cell cars from a lot of different manufacturers in the state of California. They actually give it for free, the hydrogen. So yeah, I applied for one. They turned me down, unfortunately. I won't name the car company, but I went to their website, and the deal is it was a $399 a month lease, and for $399 you get it was a very nice brand of car, by the way, which is, I would say, commensurate with any car that company would lease. If not, their standard leases would be even higher. So for $399, they pay for all the insurance, collision coverage inclusive. They pay for all the hydrogen that you would consume and all the maintenance on the car for $399 a month. But obviously high demand because they didn't get back to me. Despite all my grant writing skills, as I was filling out my 100-word essay on why I should be the one that they should lease that car to. But,
did they know you were tenured at that point?
I was not tenured at the time that I wrote that in the application, but I did try to make a convincing argument that at Stanford University we care a lot about energy. I teach energy classes. I have a lot of great conversations with students who could be potential future customers of said car, and I would show it off, but that didn't work out. I might reapply. Now there's more onto the market. I think we have time for maybe one more question. Yeah? All right. Well, thank you all very much for attending. Thank you.